Bridging the gap between digital vectors and physical reality requires a shift in perspective. You must view pixels as raw mathematical data blocks. While senior compositors understand layering and masking, standard designer workflows reach a ceiling when aiming for high-end studio realism. Technical directors approach compositing software as a mathematical physics engine, prioritizing data manipulation over visual intuition. We execute this via a specific pipeline, photorealistic MoGraph extraction. Standard software interfaces are designed for accessibility, which often creates bottlenecks in processing power and triggers VRAM crashes during complex operations. Optimization in this context requires bypasses, ignoring intuitive native tools in favor of mathematically precise workarounds. The pipeline is built on 4 specific modules: color math, spatial extraction, volumetric distortion, and optical integration. This analytical workflow is required to integrate 2D vector elements into live-action plates without overloading system memory. Every digital image relies on a foundation of color space and pixel math. The standard sRGB display-referred color space creates mathematically inaccurate results when blending light, treating color as a fixed display value rather than a physical intensity. Transitioning the project to 32 bits per channel, or float, calculates light additively. This matches the behavior of real-world photons. This chart shows the restricted sRGB triangle expanding into the wider ACECG gamut for cinematic color. Viewing this on a standard monitor creates a mismatch, breaking the colors. Adding an open color I/O display transform layer solves this, correctly routing the data. Set this adjustment layer as a guide layer. This ensures accurate working colors, while preventing the look from baking into the final render. 32-bit math demands significant processing power, exhausting RAM during the keyframing phase. Drop to 8-bit for timing, then return to 32-bit for grading. This foundation allows digital elements to act as physical light. Beyond light logic, the pipeline must account for spatial depth, specifically how foreground subjects occlude digital elements. RotoBrush version 3.0's classic calculation mode prioritizes edge precision over standard real-time playback settings. Scaling 4K footage into a 1080p composition confuses the AI engine at the sub-pixel level. The edge geometry loses alignment with the source pixels. Isolating the footage in a native resolution precomp allows precise calculation from the full dataset. One keyboard modifier accelerates AI frame-by-frame propagation. Engaging caps lock disables the visual viewer update, routing total processing capacity to the AI calculations. An active AI extraction layer must never remain inside a final master composition. Leaving it active forces continuous frame recalculation, exhausting the cache and slowing playback. Solo the extraction layer and render it as a baked asset, like a high-quality EXR sequence. Importing this baked mat as a reference reduces final render times by up to 90%. Optimization is defined by knowing when to use AI tools and when to sever them from the active pipeline to protect system speed. Integration requires forcing flat 2D motion graphics to react organically to the textures of a live-action environment. To achieve this, a flat vector shape must mold itself into the microtextures of a physical surface, such as the crevices in asphalt. Traditional displacement maps are insufficient for this. They merely stretch pixels along the X and Y axes, lacking the nuance of real physical interaction. Instead, use glass distortion effects like CC glass to read the environmental background plate. By driving the distortion with the luminance data of the live-action footage, the effect responds to the specific light and shadow values of the surface. This creates a pseudo-normal map, giving the 2D graphic the appearance of 3D volume. Because the effect uses luminance as a height map, the graphic generates its own specular highlights based on the lighting in the original plate. When using high-speed motion, avoid enabling the native motion blur switch on individual layers, as it multiplies render calculations per frame. Apply a global force motion blur effect to an overarching adjustment layer, activating it only at the final export stage. Pulling interaction data from the plate's physical luminance is the fastest way to integrate volumetric 3D behavior into a 2D engine. The final stage of the pipeline involves removing the uniform quality of digital renders through mathematical optical simulation. Depth is simulated by tying a camera lens blur algorithm to an extracted Z-depth map pass, rather than using generic box blurs. We avoid synthetic grain generators, which are slow to calculate and often produce results that do not match the sensor noise of the source camera. The difference matte grain extraction technique uses a few seconds of dark, static footage shot on the same camera as the hero plate. This equation visualizes the isolation of camera noise. By layering the dark footage over a 50% middle gray solid, we can subtract the image data. Using the linear light blending node in a 32-bit workspace isolates the analog sensor noise from the footage. Rendering a 10-second loop of this math creates a true camera noise plate. Overlaid on the master composition, it provides flawless optical matching with zero plugin overhead. A common point of failure in 32-bit renders is the out-of-memory crash that occurs as the cache fills during export. A hidden preference panel, accessed by holding the Shift key while entering the general settings, provides low-level control over memory management. Within this menu, you can disable layer caching and force the system to purge its memory at set frame intervals. This caching intervention acts as a safety valve, ensuring complex 32-bit renders complete without overloading the hardware. Mastering these 4 layers, color, space, physics, and optics, repositions you as a technical architect within the pipeline.